Welcome to lesson 27. I spent the last lesson working through 4 calculations. I'm going to begin this lesson by revisiting them. I designed the calculations so they would share words and the transition from one to the next would be comfortable. Although the questions were actually quite different, when we looked at the solutions, they all had the same logical structure. So despite having a different emphasis and numbers, these aspects of the design of the questions did not seem to change the inherent nature of the mathematical calculation. Would it matter if the questions had nothing in common? Is a mathematical solution independent from the context of its problem? So here's our review, and hopefully it will answer these 2 questions. There was a horizontal trend. It was based on the data supplied. Question 1, not enough data. Question 2, the appropriate amount. Question 3, unit values, increase the amount of work. And question 4, a lot of data because it involved relationships instead of numbers. The amount of work involved, less for question 1. We couldn't do a full calculation. More for question 4, we had to manipulate the relationships into numbers. So these were the questions. Just quickly look over them to refresh your memory. Another thing we noticed with these questions was the vertical structure is almost identical in each case. Each problem, setting, data, question. Each solution, structure of the calculation, the numbers to be calculating with, and the conclusion. And as we said, each of them can be further enhanced by a diagram showing the relevance of the specific question to other questions of the same style. So looking at the vertical trend, we had strategic management. The setting, there were details about it, data, numerical or relationships, and a question to be answered. What you did was write an appropriate equation, use the given data, draw a conclusion, using the standard solving process. In the last question, you had to be aware of the supplementary step, and in general that means draw a graph or find a second value. The problem is always tackled in this order. The first few parts are analysing information supplied. Your task then becomes to structure a coherent calculation. Remember this, it's the analysis of the problem which leads to a formula, which indicates which numbers you'll be given and how you will work with those numbers. The rest is easy. It's stuff you've done 100 times and you are good at it. Just keep in mind that to find the answer to a problem, you must know what is involved. That's determined by the keyword and the setting, and how they are linked. That involves the mathematical processes. What and how are represented by a mathematical equation called a formula when it has practical uses. You also have to know what the scale of the application is. In other words, the problem gives you starting numbers, such as how big is the square the problem is about. The fourth thing you need to know is how to convert data values into answer numbers. This is a general skill which you apply when solving every problem. Always remember, mathematical questions are very limited. The person presenting the problem must supply enough information for you to give the correct answer. The supplied information cannot be simply anything. It must contain the answer. But it might be in a modified form, and your task is to unmodify it. There is always a link between the supplied information and the requested answer. The purpose of a high school maths course is to give you an appreciation of that link. Unfortunately, the concept of linkage gets lost under the bulk of the subject. The terminology, the settings, the applications distract you from the simple connection between a problem and a solution. The purpose of this program is to unravel the subject and to expose its almost trivial basis. I'm now going to spend a little time talking about a few words which will form the basis of many of my explanations that follow. It's about how to solve maths problems. It's important that you understand what I'm saying when I use these terms. The first is keyword. This is a concept which can apply in a number of settings, such as team. The detail is different, depending upon the specific application. If we are talking about basketball, the discussion is different from when we are talking about football. But the word team carries particular meaning into both conversations. A mathematical example is the word area. This is used to indicate the surface size of a flat shape. A formula for area commonly indicates how to determine the overall size of an object, taken from a simple measurement of part of it. An area is difficult to measure, but it's easy to calculate. The second word is setting, a word which indicates special details of our task. We are working with this and not that. Different shapes can have the same area, but that area is calculated in different ways. Here, the key word is area, what we are working with. And its setting is shape, how we are working with area. Possible settings for area are rectangle, square, circle. Now, a formula. It's a word we've used before. It's a set of abbreviated instructions telling us how to do something which might be useful when we have measurements. In maths, we use a formula to describe how to calculate the value of a keyword for a specific setting from its related pieces. An example is how to calculate the value of the circumference of a circle from its related radius. A formula is a description of what's going on. The appropriate formula applies to all possible cases like this. You cannot generate this type of problem in this setting and not involve this rule or relationship. The formula relating the area of a square to its width is area equals width squared. It's impossible to make up a problem about the area of a square without involving width, which is a distance reference. We always use the formula by replacing its symbols by numbers, data supplied in the problem. How much data is required? Or more precisely, how much data must the question supply? You need a value for every variable or component, except the one the problem is setting out to find. In a difficult problem, some of the numbers might be hidden or disguised because of the words used. That is what makes it difficult. But the information is in there somewhere. You just have to find it. When you're not given enough data to replace every symbol, you cannot get a numerical solution to the problem. You get a reduced formula which applies only in that case. A true formula applies to every possible case. This can still be useful because it reduces the number of variables in the problem. How to analyse a maths problem. A formula is a description of what can happen. A problem is a description of what is happening. Therefore, everything in the appropriate formula must also be mentioned in the problem. We begin our solution process by deciding what is the appropriate formula. We identify it by examining the problem carefully and finding the key word, a general word like area, the setting, a specific word like circle, and you cannot solve the problem until you have found both. Together, they define the problem in a mathematical sense. At this stage, you know what is related and how it is related. Now we have to identify what the problem wants to know, the letter not replaced by a number. This is called the unknown. We also have to identify what the problem gives us to work with. They are the numbers used to replace letters, the data. Everything else is just the packaging or presentation, and this is often used to disguise or trick or confuse you. So a maths question gives us a lot of guidance. It gives us a keyword and a setting, which tells us which formula to use. It gives us data, which we substitute into that formula. It also tells us what is the unknown. That is the letter to isolate in the tidying up process. In our 4 problems, the keyword was total. In everyday terms, the setting was shopping. But for questions 3 and 4, in a mathematical sense, the setting was items having an individual cost. This meant that total was expressed in terms of the subtotals. So we had total cost is equal to item cost by the number of items, and we have that for every type of item that's relevant. So that makes our main formula, total cost in terms of subtotals. So we've looked at those 4 questions and we've introduced some special words. I will refer to keywords and settings frequently when discussing solutions that are to come. I'll see you in the next lesson.